Buckle in, boys, we got a good one. Hi Cherno, I started learning OpenGL seriously 10 months ago using your OpenGL and Game Engine playlists on YouTube. Wow, those are old. Here is a GitHub link to the source code. We'll have that linked in the description below in case you guys want to check it out. The project is a Minecraft clone with 10 million TNT. That's the title of this email, by the way. The project is a Minecraft clone with 10 million TNT that you can explode by going near a TNT and activating it with the left mouse button. Sounds like Minecraft. I cloned the repo from my old laptop to make sure the process is without problems. This is what I love to see. This guy has tested his code before sending it in for a code review. Why everyone doesn't do that is beyond me, because half the time nothing works. I haven't seen the code yet, but I already like this guy. Interesting points. Wow, there's a lot of information in this email. The project mainly uses compute shaders. That's cool. To render the TNT entities, I do one draw call of 10 million points. Okay, then a geometry shader checks if the entity represented by the point is visible. If it is transformed to a cube using 14 vertices, else no point is drawn. 14 vertices. I wonder why 14 vertices. I learned about geometry shaders from the book OpenGL Super Bible. Oh, that's cool. I remember reading that book when I was like first getting into this kind of stuff. The world data is stored in shader storage buffer objects. For the train, I'm using vertex pooling where I pack one side of a cube in a single entity. This is a really cool project so far. From there, using GL multi-draw arrays in direct, where one draw is one chunk. The shader goes through the array of ints for the current chunk. The TNT explosions are simplified with a BFS, like a breadth first search, I expect that means, that traverses in the same way as when the light spreads when placing a torch. This way, each TNT entity can independently check only the block it is in. If that block has an explosion level, like the light level from a torch, it quickly finds the ID of the entity that caused it, and based on the position, it calculates to what direction to be blown to. The cool thing about the BFS is that I couldn't find queues for GLSL, so I had to use an array as an alternative. Okay, I don't know exactly what this means, but maybe we'll find out. Like, are they literally talking about like a queue data structure? Because that's a bit weird, but I don't know. For the CPU to know which chunks to redraw and how many visible quads it has, I've set up a persistent map that I can easily reuse. I learned about them from the GDC video approaching zero drive over. I remember that in OpenGL from GDC Vault. How old is that? That's like very old, isn't it? I feel like this is a classic, this video. Yeah, GDC 2014. Damn, that's cool. This is a blast from the past. It was surprising how much synchronization needs to happen between everything. For example, after the quads are generated from a compute shader, I had to do a GL client wait sync because otherwise some parts of the train end up missing. Okay, that is probably an error on your part because I don't think we should be really doing anything like that. When it comes to like compute shaders, because most of this is done within compute shaders, I'm expecting that there's probably indirect draws that's actually contributing to rendering this. Yeah, I mean, like when it comes to CPU GPU synchronization and extreme sync points like this, so this function we might explore this a little bit in more detail later. Actually, to be honest, this whole project, the way that I'm seeing this looks really deep. This looks really kind of like it could be a lot to get through, like a lot of content, but it's like, I mean, I haven't seen much of it yet. Let's see if there are some screenshots. Okay, yeah, I mean, this is pretty much what I expected. Okay, cool. And then I guess it runs like for 10 million. This is probably like a tower or a cube of like 10 million TNTs. Oh, there's a video. Let's take a look at the video. Okay, so we have 1,000. We have 10,000. Objects are usually drawn with triangles as a primitive. So this is probably the geometry shader that would assemble it into that from points. And then 10 million TNT with one draw call using instancing. Ah, here it is, 10 million. Wow. Okay, so we've got like 30 FPS or so, 20, 19 FPS is falling, but wow, 10 million TNT, that's cool. I mean, I've never tried to do anything like that. I could see it being quite possible. Yeah, wow, that's really cool. Oh, that could really do with some ambient occlusion. It's very hard to tell what's going on here. Yeah, what a cool project. There's some more information here as to how explosions are handled. So each chunk has a 3D array of ints. Yeah, I mean, I think it'll probably be more fun to actually explore the code, but it's cool that there's like so much documentation here in the email as well. For this code review, I did my best to do some abstractions and clean it up, but that's where I struggle. Okay, so abstractions and cleaning it seems to be a struggle. When building a big project, what advice do you have for organizing and abstracting the code? So we can talk about that. This is my 4th Minecraft clone, and I always start over because I quickly see the issues of my current implementation and have ideas on how to improve it. For example, in my past 3 clones, the engine and game were one project. Okay, the issue was when I started over, I had to start over the engine too, which now with the 4th one, it's not the case. Okay, so you're kind of building some kind of core library that you can reuse for all these different attempts, I guess, of building this project. It will be a full circle moment learning from you OpenGL and then seeing you review this project. Well, full circle moment complete. We live at a a time where remote work is normal. Maybe you're halfway around the world with a laptop, or you're just home from the office. You're probably not tied to a single location when working. But resources often are. What do you do when you need to access those? Twingate, the sponsor of this video, is a great solution for just that. Twingate is remote access built for the modern workforce. It's a VPN replacement with a zero trust approach that lets you securely access private resources without opening inbound ports, and with much more granular, only what you need access. What if you have a Git server in the office which securely hosts all of your development repositories and you need access to that while you're out? What about your files? This is actually one of my favorite use cases. I tend to travel often, and yet my PC at home has lots of assets that I need. With Twingate, I can securely access them wherever I am, as if I'm still on my local network. Check this out, my laptop is connected to my phone's Wi-Fi hotspot, but I'm accessing my desktop PC as if my laptop was on the same network. It's as simple as that. Here's a directory from my home PC. Twingate uses peer-to-peer communication, which results in it being 86% faster than a VPN. And with end-to-end encryption plus 99.99% reliability, it's a great choice. And here's the thing, you can use it completely for free for up to 5 users, and if you don't need any of these advanced features. So go to twingate.com, link will be in the description below, and give it a try today. Huge thank you to Twingate for sponsoring this video. Thank you for all the free and amazing content. Hopefully the OpenGL series gets continued. Nah, sorry, it's a bit too late for that. A frame buffer video would rock. Also, the latest series on building application with layers and events is really interesting. That's the architecture series and helpful. I like the direction. Cool. PecaCS. You're very welcome. Thank you for sending in such a cool project. I feel like this is going to be the subject of a few videos. Again, I haven't looked at the code yet, but there seems to be a lot here to unpack. So if you guys watching are also interested in this project and you think you want to see more videos, definitely leave some comments below and I'll do my best. I think one thing that I can immediately say about this whole thing of what advice do you have for organizing and abstracting the code, this is my 4th attempt and I always start over. So on one hand, I think starting over is probably healthy. One thing that I actually used to do is, I remember when I was first learning programming, I was probably like 16, 17, I would come home from school and I feel like every night I remember sort of trying to make a game again from scratch. On one hand, you could argue like, why didn't I just continue writing that same game? I would have gotten further. I probably may have learnt more. But for some reason, when I kept like trying to do it again and again, that process, I think, of in a way iterating over that base set of code that I needed to write to get something to work, and this was like back in the Java days, that probably critically taught me that base layer, that base set of code that is the foundation of honestly any kind of project. And I think that was helpful. However, on the other side of this coin is the fact that if it's your 4th attempt of writing this Minecraft clone and you think that you keep having to start it over, and you're not sure about how to organize and abstract the code, you might also just not be implementing the complete picture until you've sort of created a Minecraft clone fully, let's just say, for the first time. You don't really know what goes into it. And if you don't really know what goes into this system, this like technical project that you're creating, it's very hard to create an effective abstraction and organize the code because you're just not sure exactly what you'll need in the future. And until you have that full big picture, how can you possibly architect something that's going to work going forward? I think based on what I've seen here, my advice to you might be to just push through this desire to organize and abstract the code and actually get the product working. Get what you're trying to make working, at least to an extent where you're like, okay, this is like an MVP. This is my vertical slice, which demonstrates some kind of set of features or a milestone of this project. And what that gives you is the understanding, this first-hand knowledge of what it actually takes for this project to do what you need it to do. What you actually have to program your computer to physically do to make this result happen. Once you have that, you can think about architecture and you can think about organizing and abstracting the code into something that's going to be scalable for the future, maintainable, reusable into an engine, all of that sort of stuff. But if you just don't have that knowledge yet, I could definitely see you adding a feature or making a discovery and then being like, okay, well, I need to re-architect this whole thing because it didn't work with this preconceived notion that I had about how I maybe thought this would work. So yeah, maybe don't give up on your design quite so quickly, complete it to some extent, and then go back and refactor it and learn from it. Okay, so here I have it open in Visual Studio. We've got a release build. Let's run it. Let's see what it is. So as shown in the GitHub screenshots, I mean, we just have, this is immediately how it launches. So this looks like, sure, this is 10 million TNTs. Can we go inside them? Oh, this is so Yeah, I mean, I'm guessing they're all here. We've just got backface culling turned off, so it's a bit hard to see. And then I'm guessing I can interact with any one of them by just clicking. Oh, yep, that's triggered that one. And then let's see what happens. Okay. Oh, there's sound. Whoa. Look at that. Okay. Performance is kind of falling a little bit. And then they're all, yeah, I mean, a lot of them are in the air. They'll just explode in the air and not affect everything. But we've also created this massive crater, which, as I mentioned earlier, really needs some ambient occlusion because it's really hard to see what's going on. That would improve the look of this dramatically. And yeah, and we've just got all these blocks here. I can click to remove them as well. So this is all fully editable. If I right click, I can't place blocks, I don't think. But yeah, I mean, that was pretty cool. And it did run quite well. So this is all implemented using compute shaders. So it's basically all happening on the GPU. I think it's going to be a really cool project for us to look at. So let's get into the code. Since the author of this code did ask for my advice on architecture, organizing and abstracting the code, I think I'm going to focus more on that, just the general application, architecture, organization, abstraction of the code base that we have over here. And then in a later video, because I really want to, and I mean, if you really want me to, let me know in the comment section below. I'm going to take a look at the compute shaders and the magic that actually makes all this happen and how that sort of works. So starting off with this, I can already see that we have two projects here aside from the dependencies. So we have a Minecraft clone and we have this voxel engine. Something else that I should probably point out as well is that inside this repository, we have generateprojects.bat using premake. So this is the premake file. We've got debug, release, and dist. So this is very familiar. This looks exactly, actually, all of this code looks exactly like my game engine series / Hazel. So that's pretty cool. It's very familiar to me. We've got all three of those configurations here. Everything's being linked in to the voxel engine library, which is over here, and then that's in turn being linked into the actual executable. C++23 is the version of C++ we're using, which is pretty cool, nice and modern. And then yeah, we just have this application, this voxel engine application inside Minecraft clone.app. The relationship between these two is correct as well. So we have voxel engine being built as a static library. There it is. And then that's being linked into the actual executable, which is our game. Inside here, we have layers, again, very similar to both the game engine series and my architecture, my C++ application architecture series, which I'll have linked up there as well. All of this stuff looks very familiar to how I write C++ as well. On tick, I wonder what the difference is between on tick and on update. They're both taken time steps, so that's interesting. And then we have our main game layer, which I'm guessing is where basically everything happens. Yep, that's a lot of lines of code. Well, relatively to the other stuff we've looked at. And there's also a lot of OpenGL functions here. Okay, so this must be, I think this is the whole, I wanted to integrate this. I didn't abstract it and hard coded it in the game where it's good to have no OpenGL code. So there's clearly some hesitation on how to maybe abstract OpenGL, which is fair enough. Oh, we got this profile scope, which again is very similar. Oh, okay, so we're using Tracy here, I expect. We've got instrumentation timers. Oh, no, we're not using Tracy. We're using, this is my old JSON. Oh, I remember this. So this is this, I believe. So the Cherno /instrumenter.h is a little gist that I have over here. And that's where this code is coming from. So this is something that you can actually open up in Chrome tracing and then see. I made a video about this like years ago. How old is this? Okay, there's 2 revisions here. So that was in, yeah, 2019. That's crazy. It's crazy to see people following the game engine series because that is such an old series. And then they're obviously doing kind of stuff that I did back then. Yeah, that's insane. What a different time it was back then, eh? Okay, so that's cool. But yes, I would definitely use something like Tracy instead. Oh, this is crazy. I'm actually really enjoying this project already just because it's sort of familiar to me. It almost feels like I wrote this because this is kind of how I would write this. I mean, especially back then, my style has obviously evolved, but the general architecture of this is my game engine series, basically. So that's really cool. And we've got source vendor over here. We've got the precompiled header. We've got this general sort of all-inclusive header, renderer, GUI, events, debug. So this is all of the actual core engine stuff we have. Yeah, even this like little Unity build of GUI files. Wow, this is just nostalgia to me. Okay, so let's kind of get back to the beginning here because I'm getting a little bit ahead of myself. So we have an application. We don't have that whole, I was going to say we don't have the entry point. We do have this entry point include. So this is, again, from my game engine series. We have a header file, which actually includes this entry point. And the rationale behind that is also got this extern create application, which needs to be supplied by the actual app. So the rationale is that the entry point point is defined clearly and lives within the actual engine, because the engine in a way should be controlling the way that the application starts up, because it has to do so many things that are related to the core application. It's the engine actually running this stuff. So therefore it makes sense for the engine to define this entry point, but obviously the entry point has to exist within the executable within the application, which is why we include it over here. And then that code will physically get compiled as part of our exe and not our static library code. But then, because we want to control what sort of application we make, we mandate ourselves to basically include this create application function, because this gets called from the main function, which is defined over here in this header file, which is part of the core engine, but you can see it's not implemented. So this is immediately going to give you a linking error unless you implement it somewhere. And the idea is you implement it over here inside the exe. And then all that application does is it pushes a layer, which is this game layer, into the application's layer stack. So application, probably not even going to look at this too much, because this is going to be very similar to the game engine series, and to even Hazel today is very similar to this. It's not quite the same, but it's similar enough that people would recognize this, I think. So yeah, this is all very familiar to me. I literally don't have to look at this code because I already know how it works and what it is. And then we have got these render commands as well, which is the beginning of an abstraction, which again is from the game engine series. Look, I mean, I have to say that in general, I'm not the biggest fan of this abstraction, even though I sort of created it in the game engine series. It might make sense for an API like OpenGL, but it's also very fine-grained and it wouldn't really translate well to Vulkan or DirectX. I can see perhaps why the author of this code struggled to also figure out how to abstract this stuff, because maybe it doesn't quite make sense. I mean, what they could have done is sort of looked at this render command and just kept adding render commands for the specific render API, which in this case, is there like a GL render API? No, not really. So render API is actually a class with these functions, and I think they're probably supposed to be virtual. Yeah, so I think in my original design, these would have all been sort of pure virtual functions that would be implemented by a class, a derived class, such as OpenGL render API, and, you know, hypothetically, Vulkan render API and whatever else, and it would sort of have the equivalent of these functions for a given render API. I mean, some of these things don't quite translate. Like, yes, you can have something like draw indexed being abstracted at that level, where it wouldn't really make sense to take in this vertex array, which is a sort of an OpenGL only concept. It doesn't really exist in other render APIs. And pretty much all of these functions would need to take in a lot more context, because OpenGL is this sort of global state machine, but the other render APIs are not. And that's one of the reasons, probably one of the biggest reasons, why most rendering engineers prefer other APIs, not OpenGL. I think I can probably take the blame for that, because the way that I chose to abstract a lot of these renderer operations, render API things in the game engine series was definitely much too fine-grained. A better example would be to look at something like modern day Hazel. And I'm not talking about Hazel 2D, the game engine series version of Hazel. I'm talking about like proper Hazel, the 3D version of the engine. So if we have a look at how this behavior, this dispatching of compute shaders and doing some synchronization, uploading, updating uniforms and everything between compute passes, how that's implemented in Hazel with all of Hazel's abstraction. Here inside the scene renderer, we have this light culling pass, which is a compute shader pass that is important to our forward plus renderer, which basically just determines which lights affect which pixels. Now you can see that we have a begin compute pass, a dispatch compute, and an end compute pass. The critical things to look at here are we have an actual compute pass, which is what we're beginning, and that sets up some base resources that are going to apply to every dispatch of that specific pass. So sometimes you'll write a compute shader and you want to dispatch it like, let's just say 100 times, but then you'll have so many resources that don't need to change dispatch to dispatch. They might change every pass or every frame. They might even never change. You might just bind them and that's it. You don't have to keep updating them. So those compute shader resources are set once essentially as part of the compute pass, and then things that actually get updated every dispatch are contained within a material. So we have two different places that we can store these resources, which in your case might be a uniform. They can be inside the pass and they can be inside the material. So this allows us to, for example, dispatch this a whole bunch of times and actually provide a different material every time. We could even update the material if we want and basically set, well, whatever we want. So there might be, you know, this u_offset that you set. We might want to set that to a different different vec3 between dispatches. And we can do that on the material like this and then dispatch using that appropriate material. But again, we can predefine these up front if we don't want to have any sort of GPU data transfer between these passes, which actually would be exactly what you would want in your case, because you can see that this offset uniform, for context, if we actually open up the compute shader, we'll be able to find it in here somewhere. Here it is, offset. So it's just a uniform vec3. So this offset variable, which we end up using for determining which chunk we actually want to work on, that you can see is predefined to these values. This should probably be inside a for loop, by the way, with just an array defining all of these permutations. But anyway, you can see that this is not dynamic data that's being generated by our program. It's actually sort of a compile time constant that we can definitely determine up front. Now, things are a little bit different in OpenGL versus Vulkan because, for example, I mean, not really, to be honest, because you could just set this up to be, the more I'm thinking about this, the more I'm thinking why this is not just an array that is inside the shader accessible at all times. I mean, you could make it a uniform buffer that you just set once and that would be it. And then based on a certain index of the actual compute pass, you could just have it access the array, which would determine which offset data to actually use. So this entire system really doesn't have to be set up like this at all. But hypothetically, using that data, you could also create a whole array of I think there are 8 of these, right? Because we have 2 possible states across 3 variables. So 2 to the power of 3 gives us 8. So you could just have an array of 8 materials and then bind the appropriate one in a for loop, and that would have your uniform data there. However, again, in OpenGL, you would still have to upload that uniform float to the shader between draws, or rather between dispatches. So I would definitely just permanently store that data on the GPU somehow and then just access the appropriate offset, the appropriate index into an array of all of this data when you need to. And then when it comes to all of these barriers, things are a little bit more complicated when it comes to Vulkan, of course, and lower level APIs like DirectX 12 would be the same. In this case, Direct3D 12, we have these buffer memory barriers, which are part of the pipeline in this version of Hazel's rendering system, but that's basically how we make those happen. So how is this all abstracted? That was sort of the original question. Well, dispatch compute is a function inside the renderer. The way that I've set this up is the renderer is this class. It's a class really just for namespace purposes because everything in here is static, as you can see, and it has much higher level concepts than what you have over here inside this render command class. So it's actually kind of similar to this because, again, this is based off of my initial design, I guess, that I created for the game engine series. But you can see that this is much finer grained. This is much sort of lower level, which doesn't translate well to other APIs, with concepts like set viewport, which doesn't really make any sense, draw indexed, and set clear color clear. Instead of all that stuff, we have much higher level things like render static mesh. I mean, what does that mean? That does a whole bunch of things. We'll also have this compute pass API where we, for example, dispatch a compute shader. And then that's implemented by a specific render API. So for example, the Vulkan renderer will implement this function. And you can see that this is actual Vulkan code. But again, there's sort of a further abstraction here with Vulkan compute pass being a specific version of that compute pass object. Vulkan compute pipeline being the Vulkan version of this compute pipeline abstraction. But we do actually end up calling actual Vulkan code over here. And then we do something like pipeline dispatch, which is in Vulkan compute pipeline. And then that is what does the VK command dispatch, which is equivalent to GL dispatch compute. Now, Hazel's backend render API, the way that we do that abstraction is actually changing. If you followed my channel this year and Hazel, you've probably heard of Renderer 2025, as I keep calling it. That's basically just changing the abstraction point so that instead of us inside Hazel having to implement each render API, Renderer 2025 is us rewriting this abstraction of graphics APIs. Instead of us actually doing it ourselves within Hazel, we're outsourcing it to be done by a rendering hardware interface layer like NVRHI. I mean, in our case, it's specifically NVRHI, but creating an RHI is good. It's kind of what we're doing here. It's just that rather us doing that and spending our engineering resources on that, we can use an existing RHI that someone else, like NVIDIA in this case, has written written, and they'll do the maintenance on that. But at the very least, it's already an existing RHI, which we can maintain going forward if we need to. It's a better starting point than doing this ourselves from scratch. In that newer version, what would happen is dispatch compute would then simply call into the renderer, which would have one implementation, and that would call into NVRHI to handle the abstraction internally within that NVRHI library. Now, the purpose of begin compute pass is to set up all of those resources. So if we have a look at what that actually does, we have sRender API begin compute pass, and again, inside the Vulkan renderer, what that will do is call pipeline begin, and then that's going to bind the actual pipeline as well as bind the descriptor set. So this is what contains our resources that are pass wide that we want to use within our compute shader. It's going to bind them for the specific compute pass that we're trying to run. So hopefully that gives you a better idea of a higher level abstraction that would make more sense, because that kind of API can exist within your voxel engine inside the renderer, inside your voxel engine, that will call into, say, OpenGL or NVRHI if you use that in the future, and actually do that work there. Now, I will say that even though I've explained that sort of renderer side of things when it comes to abstracting all of this, you should really think about whether or not for this project, it's worth it, because abstracting a renderer like this into multiple render APIs is a lot of work, because aside from just mapping these functions, I mean, even if you use like an existing RHI like NVRHI that does that for you, it does certainly make things easier, but then you're also going to have to deal with shaders. How are your shaders going to get compiled? Because they have to be different for something like Vulkan versus DirectX. In that case, a common path would be to write your shader in HLSL and then compile it into SPIR-V for Vulkan and either DXC or DXIL, depending on which version of Shrek 3D you're using. So the shader pipeline definitely gets a lot more complicated than something simple that you'll have here. And obviously you've also heard me mention Vulkan and DirectX, whereas you're using OpenGL. So if you don't have any need to sort of go in that direction, I definitely wouldn't, unless you're trying to learn about it. Potentially you just want to spend a little bit more time learning how engines work and graphics and rendering is interesting to you. That would be a good exercise, because you'll learn a lot more about how real engines handle multiple rendering APIs, which is important for the real world and for serious projects, but not for the fun of having all of these TNT explosions. You could just stick with one rendering API. If you need a little bit more control, a little bit more power potentially, and lower level control for things like performance, then you could use Vulkan. And that's obviously going to run on every desktop platform, as well as even some other platforms like mobile and a Nintendo Switch. And then you don't have to worry about this whole multiple render APIs thing with different shaders and different, it really becomes a big headache. Okay, so we've talked about the renderer abstraction. I think that that's probably a good place to leave it here for today. Here is that GL multi-draw arrays indirect function that he also mentioned in the email. And then, yeah, we just have a really simple GL draw arrays with points. So this is what draws the TNT count worth of points. So this is a big number, presumably. How many TNT to spawn? There it is, 10 million. So that's the default. Oh, by the way, you can add these like apostrophes between this to group these so that it's easier to read. So that's a little pro tip. But yeah, we have 10 million TNTs and they get spawned here. So we render 10 million points, I'm assuming. I mean, the TNTs are going to die. So this is a constant though. So I'm not exactly sure how that would work, because we probably shouldn't be rendering the initial quantity as a constant of TNTs. It's going to change. So that is a bit weird. But anyway, this is where we will presumably render 10 million TNTs as points and then have the geometry shader expanded into actual geometry, into actual cubes, so that we can do that sort of process on the GPU. And then that specifically happens for the TNTs, because here is where our terrain gets drawn. So yeah, there's lots of exciting stuff to look at here. Let me know what you guys want to see in the comment section below. Huge thank you to PecaCS or PecaCS. I'm going to go with PecaCS for sending in this beautiful project. If you guys want to send something in for me to take a look at, then send it into chernoreview@gmail.com. That email address and some instructions will be in the description below. Thank you all for watching. Till next time, goodbye.